Okay, first of all, I would like to thank Gerard and the organizers for inviting me to come here. I was here in CMU in 2002 as a visiting scholar, and I had the honor to work with Egan Ballas, and I'm really glad to be here to celebrate his life and his work. Egan has influenced lots of the careers of lots of Brazilian operations researchers, but I'm sure that Nelson Maculan can tell you more about this this afternoon. Okay, I'm going to talk about the geometric firefighter routing problem. This is a problem that arises in computational geometry. I've been trying to work with people in this field as a new frontier for applications for integer programming. So this is a joint work with Mauricio Zambon and Pedro Rezende. So this is a brief overview. I'm going to give you some introduction, talk about the first version of this problem, the geometric firefighter problem, and then the version that we are interested is the one in which we have some routing component in that is added to the problem, and talk about some experimental results and give you some final remarks. So here is what happens. We have, suppose that we have like a national forest, and there is a fire outbreak located in here. So, and we have some predefined potential barriers that you can construct to protect the forest from the fire spreading. So what happens is that assume that you have knowledge of the speed of the fire and also the speed in which you can construct the barriers. And what you want to do, let's see if it works. So the fire is spreading and you are building barriers to protect some regions from the fire. And what you want to do is you want to protect as many, the largest possible region you can do, right? So that's what you want to do. And here are the input is, of course, a polygon that corresponds to the forest, a set of barriers that you can construct, the location of the fire source, and also the speeds of the fire and of the barrier construction. So what is our goal? Our goal is to successfully construct a subset of the barriers so as to maximize the area, the area of the region that is protected from the fire. And what are our constraints? So one is that the barriers must be constructed starting from an endpoint. You cannot construct a barrier from the middle point, for instance. And there is no preemption allowed. Once you start to construct a barrier, you have to go to the end. And you cannot, well, in this version of the problem, you are not considering the possibility of constructing two barriers simultaneously. So what is, let me define what we mean by a successfully constructed point. A point is successfully constructed. I mean, if you can build this point of the barrier before or no later than the time the fire reaches that point. So for instance, you have here on your left, if you start constructing the barrier UV early enough, then you'll be able to construct point P before it is reached by the fire. Same for the final, the endpoint V. Maybe it's exactly the same time, but don't worry. We consider the firefighter will be safe because you have a factor of safety to ensure that he will be fine. Okay, here's an example of a point that is not constructed successfully because the fire reached this point P before you construct it. So a successfully constructed barrier, of course, is a barrier that is constructed. So every point is constructed successfully. And to guarantee a successful construction, what we do is the following. For instance, you cannot only look at the final point and check if it is okay to construct this point before it's reached by the fire, but you have to take into account that other points within the barrier may have been reached by the fire before you construct them. So we have to ensure that everything is constructed on time. So for this, we define the concept of a deadline, and the deadline is then the latest time to successfully construct the entire barrier that you have. So we can compute this, you know, there are some formulas that you have to use. It's a little bit complex because you know that the fire starts at some point in a polygon, then you know, you have to follow the path inside the polygon to compute this, deadlines. Okay, we're gonna use the term arrangement here because you know that the barriers plus the polygon, they define a planar subdivision, and you can think about a planar graph, and of course we use the same terms, but people in computational geometry, they will call this an arrangement. And then we have the same concepts of faces, edges, and vertices. Well, the geometric firefighter problem was studied by many people in graph theory, but we are interested in the geometric version. The geometric version of the problem was first proposed by Klein in 2014, and they had one special characteristics in this version is that the barriers must be compliant with what they call the linearity condition. Well, the linearity condition stands for the following. I mean, once a barrier is constructed, the area that is protected by, there will be an area, a region, that is protected by this barrier alone. It doesn't need any cooperation of any other barrier in order to protect some region. So here in the left side, your left side, okay, you have a linear set, so the barrier are actually chords of the polygon representing the forest, so they always protect some region by themselves. So this is not the case here, because if you think of the barriers as the segments between 2 points, you see that in fact, in this case, none of the barriers will protect any region from the fire alone. They have to cooperate. Okay. So in their paper, Klein and co-authors, they have some NP hardness proofs for many different kinds of polygon types and barrier sets. And they have an approximation algorithm with a very large constant. And we also studied this problem from an ILP point of view. And we did a lot of things like the ones that I'm going to present to you for another version of the problem. In this new version of the problem, we just dropped the linearity condition. But then we knew some other concepts. One is of a barrier path. So a barrier path is just a sequence of adjacent barriers, and which have to start on the boundary of the polygon representing the forest and end at this boundary too. So this will be something like this one. Okay, we start the boundary and then finish at the boundary. And the barrier path must be constructed following the natural path among the barriers. So you cannot start one barrier here, and then another one there, and then come back here, and so on. And of course, in this version, we also do not allow preemption. So the difference here is that we drop, with respect to the first problem, is that we drop the linearity condition. But then we have to decide how to do the routing of the firefighter when constructing the barrier. So here are the ingredients of our algorithm. We have the pre-processing procedures to construct the arrangement, because we are just given the endpoints of the barriers and the polygons, so we have to construct the arrangement. And once we have done this, we can compute the deadlines and the areas of each of the regions or the faces of the arrangement. And then we can compute shortest path with respect to the time needed to construct each of the barriers and the time that you need to get there from the boundary. The other one is our basic ILP model. So we have this barrier graph, is the graph that we will construct from the arrangement. So forget about the boundary of the boundary polygon. So then we have this planar graph And what we do is we now, this is the non-directed graph. So we're going to direct the graph by creating the two arcs corresponding to each edge. And we're going to contract all the vertices on the boundary to a single vertex, which I call beta here in this picture. And then we create two other vertices, S and D, which are just used to represent the starting, to define the starting barrier where you construct your solution, and the last one, which is the one that's going to be connected to D. And so here are the elements, the variables of our ILT. We have the arrangement A, and now for each phase G in the arrangement, we have a variable xg, which is used to say if the phase is protected or not. One, if it is protected from the fire. And if a barrier is constructed, we also have a binary variable saying if this barrier is constructed or not. And then we have a variable to represent the flow of the constructions of the barriers. So for each pair of adjacent barriers that's sharing one endpoint, barriers I and J, we have the variable Fij, which tells us if I was constructed immediately before J. Of course, we have the same for the starting point, where the starting vertex S is just for us to know which barrier we will have to start doing our solution, and to the final one, which is Fid, in the same way. And then we have these theta ij variables that we use to define, well, if this variable is 0, this means that barrier I will not be constructed immediately before J, so it gets the value 0. So this variable is 0. Otherwise, this variable will get precisely the starting time of the construction of barrier I. So the model is relatively simple. You have the objective constraints, and you want to maximize the area that is protected. Here is another, the first constraint, which says that if you have two faces that are adjacent, so what you have is that either they are both protected, or the barriers that separates, one of the barriers separating them has to be constructed. So for instance, if you have barriers I and J, I use the same different letters to denote the different directions you can construct this barrier, but if one of the faces is protected and the other one is not, this means that a barrier that separates them has to be constructed. Of course, the region where the fire source where the fire starts, it won't be protected. And then, of course, then you have like the flow constraints that you have to, once you construct the barrier, well, you have to start constructing your barriers from the boundary, so from the vertex S, and then you have to finish constructing your barrier at vertex D to denote the last one, the last barrier that is constructed. Then for each barrier, of course, depending if it is constructed or not, then you have the flow constraint saying that you have to come from some other barrier and you have to go to some other barrier, even if it is the first or the last one. And then we have the starting times for the construction of the barriers. Then here you have, there can be only one barrier constructed after a barrier I. So one of these variables will have a positive variable, a positive value, if you have constructed another barrier before barrier I, and this will take you sometimes sigma j, and then you need the starting time of the barrier j that is preceding barrier I. So this is just a relation between the starting times of the construction of barriers I and j. And then you have the deadline constraint saying that if you construct this barrier, it cannot go beyond the deadline, which is the delta I that you see there. And then you have a lower bound if the barrier is constructed. If it's not constructed, it's of course 0. But if it is constructed, then you have, this is the shortest path computed from the boundary to the barrier I, considering that Okay, you go directly from the boundary to this barrier. So this is the lower bound. And then you have the integrality of the variables except for the theta variables. The other thing we consider is to add some click constraints to this model. And this goes as follows. Suppose that for a barrier I, you compute the minimum time to get to the beginning, to the starting point of this barrier. Then you construct this barrier. Then you have the minimum time you need to go from barrier I to a barrier J. And then you have the time to construct J. So you compute this in tau ij. And you do the same for the in the other way around. If you go to J and then you construct J first and then you construct I. And of course, if these two values, they are larger than the deadlines of the two barriers, they cannot be constructed both in a feasible solution. So you must have something like that. You cannot construct both barriers at the same time in a solution, in a feasible solution. Then we also have some simple constraints, which are the maximum deadline constraints, is that if you take any subset of barriers and you look at the maximum deadline of one of these barriers, then you look at the time you need to construct all the other barriers in the set, and this cannot be, this has to be no larger than delta max, the maximum deadline in the subset. We also use some primal heuristics, and for preprocessing, we use this barrier discarding algorithms. Let me just briefly explain how they work. So we call a barrier as active if when you solve the linear relaxation of the problem, this variable, the variable corresponding to this barrier is positive. And then we have heuristics, which are ILP-based heuristics. What we do, we observe that most of the variables have value 0, so there are just a few of them with positive value. And so we have two choices. Either we set all the 0 variables to 0 and solve the remaining LP just with the barriers corresponding to non-zero variables in the linear relaxation, or we found that it's really more effective if you consider, suppose that you have all the green barriers here are the ones which are active. So what we do is that we expand this set instead of only considering these variables as integral variables and fixing all the other barriers to 0. We also add these orange ones, which are barriers that share a phase with some barrier that is active. And finally, of course, we also have a very simple discarding procedure for the barriers, which says that, I mean, of course, if the fire reaches the barrier before the deadline, you can do anything. This is just an easy computation that you can do and see what you get. I mean, if it's possible to construct this barrier or not. Okay, this is our computational environment, very standard one. I have to say that we use a lot of Siegel, which is a library for computational geometry, algorithms, and data structures. And also an observation that we let our IP solver to run for 30 minutes to solve the model and to use them as heuristics just 60 seconds, 1 minute. Okay. Okay, we have two sets of instances. These instances were constructed from US National Forest, which is the polygons corresponding to the US National Forests. And then to create the barriers, what we did, we had two sets of instances. The first set of instances, we just randomly created some points in the interior of the polygon. You create the Voronoi diagram, and you use the edges of the Voronoi diagram as potential barriers. Right? But the problem with this kind of instance is that most of the vertices will have degree 3, as you know. Okay? So it's a Voronoi diagram. In most cases, the vertices are going to have degree 3. So to avoid this, then we created instance in another way. We constructed Delaunay triangulation, and we removed some of the edges in the Delaunay triangulation to keep the same number of barriers in the two instances. The instance from T1 and T2, they all have the same number of barriers. And we also create some situations to force some vertices to have degree much larger, even much larger than 3. Okay, so in total we have 1,200 instances with different, for different polygons, and we have different fire speeds and just one speed for the construction of the barriers, and this was the only one in which, the only case in which the fire speed is smaller than the barrier construction speed. So this is what happens. First of all, the barrier discard, how does it work? So as expected, if you look at the first column and the last one, first column, the fire is very slow. The last one is really going fast. So of course, if the fire is going very fast, many of the barriers you won't have time to construct. So you eliminate most of them. And on the other opposite, you have the situation where you eliminate very few of them. It's about the same in the two sets of instances. This is an idea of the number of barriers you have. So just to give you an idea of the size of the ILP, remember that the number of variables we have and the number of constraints is polynomial sized in the number of barriers. So these are relatively huge models. And this is what happened. So let me explain this notation here. This is the model. Oh, the first letter is always B. We are using our first model. The H here means if you are using the heuristic or not. The C here means if you are using the click inequalities or not. And the D ones mean that if you are using the deadlines or not. You can see from here, this is the percentage of instances that were solved. And you can see that, of course, because we have eliminated lots of barriers in this side, so it's the easiest instances are there. So the most difficult ones are here. So just focus on the first column. And you see that how the contribution of every thing that we added to the algorithm. So if you compare the two first rows, you see that just by adding the click constraints, you get much more instance solved. But the huge impact comes when you add the click inequalities and the deadline inequalities. And if you put everything together, then you get a little bit more. So definitely the instances where the fire speed was small was the most difficult. And here you see that the fact that we have added vertices with larger degrees makes the instance even more difficult. So you see that the percentage of instances that were solved is much smaller in the second case. Well, here's for the impact of the heuristic, just look at the last line, use all the heuristics, and you see that many times the heuristic is very successful. It's just 60 seconds the heuristic had to do that. It's just very successful. I mean, more or less 80% of the cases were solved for T1 and for T2 a little bit less. Again, the instances where you have larger degrees are more difficult. So this is the graph for the times. This is a log scale, while this is T1 instances and T2 instances. This is the number of barriers after the discarding procedure. You see that the time, okay, it grows exponentially, but the blue ones were around 35 minutes. You see that most of the instances were solved in less than 5 minutes. And you see that the straight line here is a little steeper for T2 than T1. Again, T2 instances are more difficult. So for the final remarks, okay, what we tried to do here was to make the problem a little bit more realistic. Like, okay, usually you don't have the linearity condition. We try to make it more realistic, but still there is some work to be done because we have, first, you can consider the use of non-constant fire speed and barrier construction the same. So the fire changes speed as it's going on. Of course, we haven't considered that once you construct a barrier, you divert the fire, so maybe the deadlines will get larger. We are not doing that, but it's interesting. Okay, so anything you might think that making this model more realistic, but it was our attempt to make it more realistic compared to the previous work. And if you want to know more about this work was published in European Journal of Operational Research this year. And I also have in my website all the instances and solutions for all these instances. Everything is available. Okay, so thank you very much.